Hello everyone, Assalamualaikum warahmatullahi wabarakatuh, and good day to every one of you. Welcome to my video. So basically this is a continuation of a lecture video on the chapter of transformer. Okay, so my name is Dr. Norzulaili binti Muhammad. So this is my email address. You can just feel free to email me whenever you have a question regarding the content of this video. Okay, alright. So basically, in this video, we are going to continue our topics on ideal transformer. Okay. So let's move to the subtopic of today, which is ideal transformer. Okay. So for the ideal transformer, so you can consider you have a transformer with two windings, such as shown in this diagram. Okay. So basically, this is the schematic diagram of the transformer that have two windings. Okay, you have a primary windings here with N1 turns. Okay, and then you also have a secondary winding of a N2 turns. Okay, and then basically it is common to show that the two windings are the two legs of the core. Okay, although in the actual transformer the winding is actually interleaved to each other, but we just consider for your other transformer, the first winding is tied at the first core and then at the first leg, and then the second winding is tied at the second legs of the core. Alright, so for the ideal transformer, we need to consider the following properties. Okay, so the first thing we need to consider is a winding resistance are negligible. Okay, so here you have a winding, here also you have a winding. We consider the resistance of the winding are negligible. Okay, and then we consider that no leakage reactance, meaning that all flux, okay, these flux are confined to the core. Okay, and then all flux are linked both windings, so there is no leakage flux. And then we consider the core losses also negligible. Okay, core loss equal to 0. Okay, and then for the third properties, the permeability of the core is infinite. So therefore, the exiting current is negligible. And then the net MMF is equal to 0. Okay. Okay, so you consider this schematic diagram when the primary winding is connected to the V1. Alright, so the time varying flux of dphi over dt will be established in the core. Okay, so due to that, the E1 will be induced in the winding, and this E1 will be equal to the V1. Consider the resistance of the winding is negligible. So that's why, in this case, V1 is equal to E1 equal to N1 multiplied with d flux over dt. Okay, and then for V2, because you know the core flux, okay, this core flux will links between the primary winding and then the secondary winding, and those it will induce the voltage of E2, which is same as per V2. So that's why here you have V2 equal to E2 equal to N2 multiplied with d flux over dt. And then you can divide equation number 1 to equation number 2, so that you have V1 divided by V2 equal to E1 divided by E2 equal to N1 divided by N2. Okay, so in this case, d flux over dt divided by d flux over dt, we can cancel out. So all this thing will be equal to A, where your A is a turns ratio. Okay, and then next, now we connect the load ZL to the secondary winding by closing the switch. Thus, it will cause I2 to flow through the secondary winding, and then consequently the MMF will be induced, where the MMF is equal to N1 multiplied with I1 equal to N2 multiplied with I2. Okay, and then you can rearrange this equation so that you have N1 divided by N2 equal to I2 divided by I1. So in this case, the equation we consider as the equation number 4. Finally, based on the equation number 3 and equation number 4, you can have V1 divided by V2 equal to E1 divided by E2 equal to N1 divided by N2 equal to I2 divided by I1 equal to A. Alright, so this is basically the general equation for the ideal transformer, where your A is represent the turns ratio. Okay, so this equation you need to remember in order to solve the problem with the ideal transformer. Okay, And then next we go to the second topic, which is impedance transfer. Okay, so we are going to see what is the impedance transfer actually, what is the concept of the impedance transfer, and then how to do the impedance transfer for the ideal transformer. Okay, so the impedance transfer is used in simplifying the circuit that involve the transformer by transferring the impedance from one side of the transformer to the other side. Okay, so you assume that you have this kind of ideal transformer, and then you have a Z2 that connected to the secondary winding. Okay, so here you have a first winding, and then here is secondary winding, and then the secondary winding is connected to the Z2. So the purpose of the impedance transfer now, we need to transfer the Z2 from the secondary winding to the primary winding. Okay, so in the end, we have this kind of circuit where V1 is directly connected to the Z2. Okay, by neglecting the winding here. Okay, so this is the purpose of impedance transfer. Okay, so this is the general equation of the transformer where you have V1 divided by V2 equal to N1 divided by N2 equal to I2 divided by I2 divided by I1 equal to A. A is the turns ratio. Okay, alright. At the secondary winding, here you have a Z2. Okay, so the secondary impedance of Z2 is given by V2 divided by I2. Okay, Z2 equal to V2 divided by I2. Okay, and then at the input impedance, which is Z1 will be equal to V1 divided by I1. Okay, so based on the general equation of the transformer, you know V1 will be equal to A multiplied with V2. So that's why here A V2. Okay, for I1 will be equal to I2 divided by A. So I2 divided by A. Okay, and then we can rearrange this equation so that you have A and A. So here I have A squared multiplied with V2 divided by I2. Okay, so V2 divided by I2 is actually represented by Z2, right? So here you have A squared multiplied with Z2. Okay, so here A squared multiplied with Z2 will be equal to Z2 prime. Okay, so Z2 prime equal to A squared Z2 is actually the secondary impedance seen from the primary side is denoted as a Z2 prime. Okay, so if the Z2 is located at the secondary winding, so we call it as a Z2. But if the Z2 we transfer the Z2 to the primary side. Okay, so the secondary impedance Z2 will be denoted as a Z2 prime, where the Z2 prime is equal to A squared Z2. Alright? Okay. Okay. So, this equation based on the previous slide, Z2 prime is equal to A squared Z2. So, this is actually the impedance that transfer from secondary to primary. Okay. If you have a Z2 connected to the secondary, and then you need to move the Z2 to the primary side. So, the new Z2 will be Z2 prime, where the value of Z2 prime is equal to A squared Z2. Okay. Alright. So, impedance Z2 that connected in the secondary will appear as a Z2 prime as looking from the primary side. So, finally, we can conclude that impedance can be transferred from secondary to primary. Okay, in this case, you transfer Z2 from secondary to primary if its value is multiplied by the square of the turns ratio. So, here you see, you multiply the Z2 with the square of the turns ratio, and then you can just move the Z2 from the secondary to the primary side. Okay, and then the new impedance will be seen as a Z2 prime. Okay. Okay, so the impedance actually can move from one side to the other side. It's not necessary from secondary to the primary. Okay, so impedance from the primary side can also be transferred to the secondary side. And in that case, its value has to be divided by the square of the turns ratio. Okay, remember just now you transfer from the secondary to the primary. In that case, if you transfer from secondary to the if you transfer from secondary to the primary, the value you need to multiply with the square of the turns ratio. But if you want to move from primary to the secondary, then its value need to be divided by the square of the turns ratio. Okay, so how to prove that? So based on the general equation of your ideal transformer, you know that V1 divided by V2 equal to N1 divided by N2 equal to I2 divided by I1 equal to A. So this is the general equation of the ideal transformer. Okay. And then you know your output impedance now is Z2 equal to V2 divided by I2. So based on the ideal transformer, you can substitute into here where you have V2 is V1 divided by A. Okay, V1 divided by A. And then I2 in this case is equal to A multiplied with I1. A multiplied with I1. Okay, so, and then I can further simplify this equation so that I have 1 over A squared multiplied with V1 divided by I1. Okay, so V1 divided by I1 is equal to Z1. So in this case, Z1 divided by A squared. Okay, so here, if I remove my, if I move my impedance from the primary side to the secondary side, so the new Z1 will be denoted as a Z1 prime equal to Z1 divided by A squared. So the value has to be divided by the square of the turns ratio. Okay, so the new Z1 prime will be equal to Z1 divided by A squared. Okay, so Z1 prime is actually the impedance that transferred from primary to the secondary. Okay, right. So let's have a look at the following example on how to solve the problem on the impedance transfer. Okay, so you consider you have a speaker of 9 ohm connected to the supply of 10 volt with the internal resistive impedance of 1 ohm. Okay, and then you need to determine the power absorbed by the speaker. Okay, and then next, to maximize the power transfer to the speaker, you use a transformer of 1 to the ratio of 3. Okay, so the winding ratio here, 1 to the ratio of 3, is used between the source and the speaker as shown in the figure B. Determine the power taken by the speaker. Okay, so let's see how to solve this question. First, we need to determine the power absorbed by the speaker. So based on this circuitry, you know that I will be equal to V divided by total of R. In this case, total of R is 1 ohm plus 9 ohm. Okay, so you have 10 divided by 1 plus 9. So 10 divided by 10 is 1 ampere. Okay, and then once you know the value of I, then only you can find the power where P will be equal to I squared R. So in this case, I is 1 and then total of R of the speaker. Okay, because power absorbed by the speaker. So that's why R of the speaker is 9 ohm. So 1 squared multiplied with 9 is equal to 9 watt. Okay, and then settle for A. How about B? For B, the question is to maximize the power transfer to the speaker, we use the transformer here. Okay, so the transformer is used between the source and then the speaker. So determine the power taken by the speaker. So the goal here, we need to transfer the impedance from the secondary side to the primary side. Okay, so we need to find the value of the new R2, where the new R2 will be equal to the R2 prime. Okay, so if the resistance of the speaker is referred to the primary side, we move from the secondary side to the primary side. So the new R2 here, R2 will be equal to R2 prime. So R2 prime is equal to A squared R2. So A in this case is a N1 divided by N2. So 1 divided by 3. So A squared 1 over 3 squared multiplied with R2 is 9 ohm. Okay, so you just do the calculation. You get R2 prime is equal to 1 ohm. Okay, so this is the new circuitry that you, after you move the you move the impedance from the secondary side to the primary side. This is the new equivalent circuit. Alright. Okay, and then based on this, you can calculate the power. So the new I will be equal to 10 multiplied with 1 plus 1. Okay, so equal to 5 ampere. And then finally, the P equal to I squared R. I is 5. Okay, 5 squared multiplied with R. Speaker is 1 ohm now. So 5 squared multiplied with 1 equal to 25 watt. Okay, alright. So you can see that after you use the transformer, you can maximize the power that transfer to the speaker where you have a 25 watt. But if you refer to the previous slide, okay, you don't use the transformer, the power that absorbed by the speaker is just 9 watt. Okay, so you can see lah, whenever you use the transformer, you can maximize the power transfer to the speaker. Okay, where the value now is 25 watt. Alright, so that's all for now. Thank you for watching my video. I'll see you in my next video, okay? Bye!